Today we're going to talk about the t-test for two related samples. A repeated measures design, or a within-subject design, is one in which the dependent variable is measured two or more times for each individual in a single sample. You can think of it like classroom A, and then you give them a pre-test and you give them a post-test. This is a repeated measures design. The same group of subject is used in all of the treatment conditions. On the formula sheet, the third column of equations will be used, so go ahead and get out your formula sheet now. In a matched subject study, each individual in one sample is matched with an individual in the other sample. The matching is done so that the two individuals are equivalent or nearly equivalent with respect to a specific variable that the researcher would like to control. An example, you would match someone in classroom A who made an A on the midterm with someone in classroom B who also made an A on the midterm. So repeated measures and matched subjects design use the same set of equations. The data consist of two sets of scores for each pair of subjects. N is considered the number of pairs of scores. So if you had a classroom of 20 people and you gave them a pre-test and a post-test, N would be 20. If you had a classroom of 20 people and then you had another classroom of 20 people and you matched them across some similar variable like midterm grade, N would still be 20 because it's the number of pairs of scores. For example, here's an example from a repeated measures or a matched subjects design where N is equal to 5. So there are 5 matched pairs. There's the first score column, there's the second score column. Because the scores are in one set are directly related with scores in the second set, the two research designs are equivalent and share the common name of related samples design. So repeated measures and matched subjects design are all under the umbrella of related samples designs. The t-test for a repeated measures research design is very similar to the t-statistics we examined for a single population, single sample with the population, the first set of equation column on your formula sheet. The major distinction of the related samples t-test is it's based on different scores, which give you a D, rather than raw scores, which give you an X. Otherwise, you'll notice the equations are almost identical. For the repeated measures design, the sample data are different scores and are identified by the letter D rather than the letter X. To find the different scores, you just first list the subjects, for example, 1, 2, 3, and 4, or A, B, C, D. Then you list the two columns of data that you've collected, first test, second test, pre-test, post-test, however it works. Then you make a D column, and you just subtract whichever column has most of the higher scores. That's the column I pick, and I start with that one, and I subtract off the lower scores. Some columns will be a little bit flipped, like column B here has a score of 15 for person B and a score of 13 on test 2. So you would get a negative answer for that one, and it's fine. Negatives are fine because we're going to be squaring all the D values, so it really doesn't matter. So step 1 of finding a problem is you would find D. Step 2 is you would find the mean of the different scores. This is equivalent to, in the first column of equations, finding X. And then once you have your X column, then you find the mean, which is just the mean of the summation of the scores over N. Same amount works here for this problem. So these are reaction time measurements, taking before and after taking an over-the-counter cold medicine. So person A, notice before medication is 215 and after is 210. Person B, C, and D also have scores. Notice most of the scores are higher on the after medication, so I would take the after minus before. So, and find the difference. After minus before, notice the first one is negative, but the rest are all pretty positive numbers in their 20s. To find the summation of D, you add up the D column. And to find the mean of D, you would just say summation of D over N. And remember again, N is just how many pairs you have. In this case, there are 4 pairs, there are 4 people. Let's look at the hypothesis for a related samples t-test. The hypothesis just says the mean difference is equal to 0. That means there's no difference between the first set of scores and the second set of scores. The research hypothesis says the mean difference is not equal to 0. So there is a difference between the first set of scores and the second set of scores. Remember, this t-test only uses 2 sets of scores. Here's what the t equation looks like. You can find it on your formula sheet. T is equal to m sub d minus mu sub d over s sub m sub d. So mean minus mu over the estimated standard error of the mean difference scores. In this formula, the estimated standard error is computed exactly the same way as it is for a single sample t-statistic. The first step is to compute the variance for the d scores. The estimated standard error is then computed using the sample variance and the sample size n. Here's another example. Ratings of pain for particular participants saying neutral word or a swearing word. So these are their pain levels. When they say a neutral word, then they give us their pain level. When they say a swear word, they give us their pain level. So we want to know which one's higher or lower. So in this case, the researcher says they think swear words are going to be higher, so they do swear word column minus neutral word column. So for each person, see participant A, would be swear word is 7 minus the neutral word of 9. 7 minus 9 would give you -2. So you would go through the whole participants from A all the way down through I and calculate a D score for each one. The next thing you would do is you would find D squared. So you would square each of these D values. So -2 squared is 4. Remember that a negative number squared is always positive. So your D squared column will only have positive numbers. Then you would sum up these 2 columns. Just as if they were an X and an X squared column, now we have a D and a D squared column. So the summation of D for this column is -18. The summation of D squared is 68. The mean of the different scores is just summation of D over N, so -18 over 9. There are 9 participants or 9 pairs. We give you -2. Then we would find the sum of squares. Just like we did for X, we now have a new sum of squares equation using D. So summation of D squared, which is the big number, is 68, minus summation of D, which is the smaller number, -18 squared over N, which is 9. That would give you a sum of squares of 32. And you could work your way down through the equations. Here's some assumptions of the related samples t-test. It requires 2 basic assumptions. The first one is that observations within each treatment must be independent. Okay? It refers to the scores within each treatment. So, for example, the same person couldn't take 2 pre-tests. Okay? The population distribution of the different scores must be normal. This is the assumption of normality. When we talk about effect size, we use Cohen's d and r squared, same as we did before. For d is equal to m sub d over s, and r squared is equal to t squared over t squared plus df, same as the previous chapters. The size of the treatment effect can also be described with a confidence interval. Again, same type equation, except instead of m, you have m sub d, plus or minus t times s sub m sub d. Same exact equations, we're just using column D to find our answers instead of X. Comparing repeated and independent measure designs. A repeated measure design requires fewer subjects than an independent measures design, because you can use a before and after. The repeated measures design is especially well suited for studying learning, development, or other changes that take place over time. The primary advantage of a repeated measures design, it reduces or eliminates problems caused by individual differences, because the same person is taking before or after, or if you're doing matched subjects, then it will be the same pair matched on some construct. Individual differences are characteristics such as age, IQ, gender, personality. These individual differences can influence the scores obtained in a research study, and they can affect the outcome of a hypothesis test. So definitely if you have repeated measures design where you're using the same person, well, the same person has the same age, the same IQ, the same gender, the same personality, because it is exactly the same person. The primary disadvantage of a repeated measures is that the structure of the design allows for factors other than the treatment effect to cause a participant's score to change from one treatment to the next. For example, maybe they learned something new. Maybe there's two different conditions of living. So maybe each individual is measured at different times. So maybe they are hungry for the second one. You don't know. One way to deal with time-related factors and order effects is to counterbalance the order of presentation of treatments. That is, the participants are randomly divided into two groups. One group receives treatment A first, followed by treatment 2. The other group receives treatment 2, followed by treatment 1. For example, if I wanted to give you all a pre-test and a post-test that are basically equivalent tests with just slightly different questions, I would divide my classroom in half and give part of you test 1 first, the pre-test, and part of you the post-test first, and then I would flip it. So the goal of counterbalancing is to distribute any outside effects evenly over the two treatments.